In this very short video, let's do this. Let's build a very simple model for, let's say, assessing credit risk. Let's say we are measuring credit risk using a measure like the credit VAR. For that purpose, what we need is a loss distribution. And in this video, we'll try and get something like an expected loss, which is like the mean of this loss distribution, and the unexpected loss, which is like the variability or the dispersion of my loss, which means it's the standard deviation of my loss distribution. So let's do this. Let's first begin with the key ingredients or inputs that we will need. The first input that we need is what we refer to as the exposure amount. Think of the exposure amount to be the loss that you will incur when your counterparty defaults at any given point in time. Now, when we've touched upon time, let's do this. Let's fix some horizon over which we'll be building our loss distribution. So typically speaking, when we compute the credit VAR, the horizon which is chosen is 1 year. So I'm assuming here that the exposure amount is the loss that you will incur when the counterparty to your position defaults. And here I am talking about default, let's say, which happens at the end of 1 year, for example. Okay. Now, at this point, let's make a distinction. The first distinction is your position a loan? If your position is a loan, then computation of the exposure amount is actually relatively straightforward. What you stand to lose at the given time slice or at the end of the horizon, if your counterparty were to default then, is, let's say, the outstanding principal balance plus any unpaid interest. Things become complicated in terms of exposure computation if your position is, let's say, a derivatives position. The reason for that is, let's say if I am trying to compute the exposure, let's say at the 1 year time point or 1 year time slice, then the valuation of my trade at that point in time will actually depend on the evolution of the core risk driver of this trade, or drivers if there are multiple of them. So I'll have to first simulate my risk drivers, plot something like an exposure distribution, and then maybe take a mean of that distribution and work with the mean. So therefore, I am for this simple opening video on, let's say, credit risk modeling, I'll just stick to a simple case, and that simple case is a position like a loan or a bond, for which, as I said, the computation of the exposure is relatively straightforward. The next input that we will need is the probability of default. Again, it's an input which depends on the choice of the horizon. Why? Because the probability of default will scale by the horizon, or scale with the period over which this probability of default is estimated for. So again, I'll be assuming, let's say, 1 year period. Two things to keep in mind here. This probability of default will depend on factors such as macroeconomic factors. And the second thing is that this probability of default will also depend on factors which are specific to your borrower, okay, or your counterparty. So one determinant of probability of default is, let's say, the rating of your counterparty, just in case your counterparty is being rated by some rating agency, or let's say even internally by your bank. So this was about probability of default. The third input that we need is a loss rate. Think of this to be the proportion of, let's say, $1 of the exposure that you stand to lose if your counterparty defaults. Okay, so we can define another measure which we refer to as the recovery rate, that is 1 minus the loss rate, and you can define it verbally as the proportion that you stand to recover. So loss rate is the proportion you stand to lose, recovery rate is what you stand to recover. If you were to take these three inputs, take a look at these three inputs, you will see that this input is basically related to the incidence of default, while these two some ways, put together, give you a handle on the severity of the loss. So this one is your total exposure amount. This one is the loss on a per dollar basis. If I were to somehow multiply the two, this will give me a handle on the loss severity. Okay. Now, for this particular, model that we are trying to build, a very simple one actually, we are trying to capture the variability of the loss rate here, but not necessarily the variability of the exposure amount. So when I say variability of the loss rate, then I'm assuming here that loss rate is not really a constant. I'm assuming that it's a random variable with a certain distribution, and that distribution, let's say, has a mean given by LR bar and a standard deviation given by sigma of LR. Okay. Now let's start building our model. So our model, what it will do is, very simply put, it will try and capture two future states of the world, and let's say which of the two states finally reveals itself, let's say we get to know that after the end of our horizon, which I said is 1 year. So we are capturing that, two states of the world. One can be default, one can be survival, by a Bernoulli variable. Let's call that variable D. So I'm assuming here that D can take two possible values. When D takes on a value 1, it's a state of default. That state materializes, let's say, with a probability PD. If the counterparty survives, that counterparty can be, as I said, a derivatives counterparty or your borrower, then that state of the world, let's capture it with a value of D to be equal to 0. And this state materializes with a probability 1 minus PD. Now let's write down the loss that we incur in both these states. If your counterparty defaults, then we said that the loss that you incur is the exposure amount scaled appropriately by the loss rate. Okay. So that's your loss. Since D is equal to 1, I can very well incorporate the D into this formula for the loss, and still it stays unchanged. D is 1. Okay. Now let's do this. In the state of survival, our loss is 0. We do get paid what we are owed, and therefore the L, we write it as 0. Since D is equal to 0, I can very well write the L to be D times LR times EA. Since D is 0, I don't care what the LR and EA are. Okay, the loss still turns out to be 0. So net, what we've achieved by this very simple model is that the loss, which I know is random, I do not know what my loss will be at the end of the horizon. All I am saying here is let loss be the product of, ideally speaking, three random variables: D, which determines default, LR, which determines the loss rate, and EA, which determines the exposure. Now, in general, as I said, for a complex derivatives trade, this is not known to us, it's random. And then LR we know is random, D is random. So I said L is a product of three random variables. Before we move ahead, let's make a few assumptions. These assumptions will come in handy when we derive the expected loss and the unexpected loss. The first assumption that I am making here is, which is something which I have already made actually, and that is that the default event basically involves just two states of the world. It can either be default or it can be survival. There is no third kind of state. That's my first assumption. My second assumption is that my random variables LR and D, let me assume that they are independent, which means that the factors which affect the severity of the loss as captured by the loss rate and the factors which affect the incidence of loss, which is my Bernoulli variable D, let's assume that these factors are statistically independent. That means these factors do not influence one another. There's no commonality of factors in determining the two random variables LR and D. That's like verbally putting the statement. Then something which I've already said before also, let me restrict myself in terms of EA. Let me not really capture the variability of this EA. Let me just work with something like an expected amount if it's a derivative, or let me just work with, a simple position like a loan or a bond. Let me restrict the type of positions I'm working with. So I'll be capturing the variability which comes from LR and D, but not really variability which comes from EA. Okay, so let's do that. Let's try getting our first result, which is the expected loss. Expected loss is the expectation of my random variable L. I have defined L to be a product of three random variables, exposure, D, and LR. Exposure comes out. I have made a lot of restrictive assumptions about the exposure, and we are then left with the expected value of the product of D and the LR. My second assumption told me that let me assume that D and LR are independent. That means I can write down the expected value of their product to be the product of the respective expected values. What is the expected value of D? D is a Bernoulli variable, therefore its expected value is P. Remember the probability of success. If you were to write it down explicitly, it's basically 1 times PD. The first possible value is 1. The second possible value is 0. That times 1 minus PD. Okay, so the answer is the expected value of D comes out to be PD. We have already said that the expected value of LR is LR bar. So this is my expected loss. Now let's take a look at unexpected loss. First thing which I want to qualify here is that unexpected loss in different models and to different authors means different things. For this particular reading and this introductory credit risk model that we are doing, let's just intuitively sort of take the definition of unexpected loss to be the variability of losses around the mean, something which we know is the standard deviation, variability or dispersion around the mean. Okay, so this choice of unexpected loss as the standard deviation may not necessarily be a very good choice, especially because in the case of credit risk, my loss distribution is generally not as symmetric as what you encounter in market risk, for example. It's a pretty asymmetric distribution. Still, let's not debate that here. Let's proceed with our choice of unexpected loss to be, let's say, standard deviation of my loss distribution. So let's do that. So variance of my L, which is my random loss, I know is the expected value of L squared minus the square of the expected value. Let's find out this guy. This guy we already know. So expected value of L square will be the expectation of EA square times D square times LR square. So each one of these is like a function of the random variables that we've encountered here, D, LR, and actually EA also. Let's bring the EA term out. So it will be EA square times the expected value of D square times the expected value of LR square. Again, I have imposed that assumption that D and LR are independent random variables. So what is the expected value of D square? It will simply be 1 square this times PD plus 0 square this times 1 minus PD. So that means it's PD. That's expected value of D square. What is the expected value of LR square? We can get this from the definition of the variance of LR. So the variance of LR I know is simply the expected value of LR square minus the expected value of LR whole square. So I can get this term on that side and I can write down my expected value of LR square to be the variance of LR plus the mean of LR squared. Okay. Now, if you were to simplify things a bit by substituting expected value of LR square into this formula, you will end up with this expression. Take a look at the last two terms. So these two terms, if I take the mean of LR square common, I get PD minus PD square, which is basically PD times 1 minus PD. And recall that this is the variance of a Bernoulli random variable D. Remember the variance? It's PQ. Probability of success, this times probability of failure. So I can then, write down this PD minus PD square to be just sigma square D. Remember this to be the variance of a Bernoulli variable D, which captures the incidence of default. So this is my variance of the loss distribution. Take a square root and what I have is the standard deviation of my loss distribution. So what we've done here, very quickly in a very short video, is we have built a very simple credit risk model one which only has two possible states in the world, one which only focuses on a single position, a single credit, a position in which we are not really worried about the variability of EA, but we are trying to capture the variability of the severity of loss as well as, let's say, the incidence of loss. And what we have in front of us are formulas for the expected loss and the unexpected loss.